Hello everyone. The following notes are going to cover 16.4 to 16.5, mainly dealing with acid strength and the pH scale for strong acids and strong bases. We'll get into weak acids and bases later. Acid strength is determined by the relative amount of hydronium, or H+, that gets produced. And one way to quantitatively measure this is by using the pH scale. So there are several ways which we can assess acid strength. pH scale is one of them. Let me show you a few things before we get into the pH scale. Acid strength can be measured or assessed using one, the pH scale. However, the pH scale can be a little tricky because it's concentration dependent. We can use percent ionization, which is also concentration dependent. And third, we can use the Ka value for an acid, and that is independent of concentration. So we're going to look right now at the pH scale. What does it mean? How do we use it? What does it tell us about acid strength? All right, so let's take a look at the following table. Now, I hope that we have a basic understanding of autoionization of water from the last section. If you recall the autoionization of water, we have two water molecules that can react to give H3O plus and OH minus. Right now, in a sample of pure water, if you remember, based on the Kw, expression, right? Kw, the equilibrium constant for water, which is the product of the hydronium and the hydroxide from the equation above, is equal to 1.0 times 10 to the negative 14th. This is at 25 degrees Celsius. So that means the hydronium and hydroxide are both equal to 1.0 times 10 to the negative 7th molar at 25 degrees Celsius for a sample of pure water, right? They're the same in a sample of pure water, and if the product is 1 times 10 to the negative 14th, then they have to be equal. So if we look at our table, an acidic solution means you've got more H plus or more hydronium than hydroxide. In pure water that is neutral, they're equal. H plus equals OH minus. And a neutral solution has a pH of 7. Your H plus as well as your hydroxide in pure water is 1 times 10 to the negative 7. And the color of litmus paper will be relatively neutral. On the orange litmus paper that you used earlier this year, which was orange, water would not change the color. So back to the acidic solution, we know that the H plus is greater than the hydroxide. The pH is going to be less than 7, and your H plus means it's greater than 7. So for this Ka equation, for an acidic solution, H plus or hydronium is greater than the hydroxide. Now, if you look at the equation, Kw, the value is a constant. It can't change. So if the hydronium goes up, then the hydroxide must go down. Vice versa. If the hydroxide goes up, then the hydronium has to go down to maintain that constant value. So when we go to a basic solution, one that has more hydroxide than hydronium, with a pH greater than 7, the H plus has to be less than 1 times 10 to the negative 7th, because if the hydroxide goes up, hydronium goes down. Acids turn litmus pink, bases turn litmus blue. Here's your general pH scale. All right, it goes from 0 to 14. 0 to 7 is acidic. 7 to 14 is basic. So where does this pH scale come from? Well, it's generated from that logarithmic function, and we're going to talk about these equations in a moment. But hopefully, from your reading, you saw that the pH is the negative log of the H plus or hydronium ion concentration. So this scale, what the pH means, just being a logarithmic scale, right? These are log base 10. What this function, this logarithmic function does, pH, is it takes really large and really small numbers and squishes it into a smaller scale. And that's how we arrive at the pH scale. That 0 to 14 really comes from all the possible values for acids and bases in water, right? Their concentrations plugged, the concentrations of the hydroxide or hydronium plugged into equations that generate this scale. So all you have to know how to do is how to calculate the pH. Now, this scale is a little misleading. There are negative pH values under certain circumstances. We're not going to go there. I'm not going to give you those problems. We're going to be working with things that fall within the general range from 0 to 14. All right, so here's how we do some of these pH calculations. All of these equations come from the autoionization of water and the Kw expression in that original equation. It's all based on that. However, let's just look at how we use these. The map is going to help you navigate all of the calculations. Remember how we have the mole map where we just follow the direction? If you stay in the right-hand lane, it will tell you the equation to use, except obviously for up here, there's only one equation on the top, one equation on the bottom. But with these, you're given a variable, you just plug whatever you have in and solve for the third, or solve for the other variable. So, for example, in exercise 5, if you're given the H plus, we have to calculate the pH, pOH, OH minus, and determine if this is acidic or basic. Here's how you approach this problem. If you're given the H plus, look, this is where you're at on the map. What's the easiest thing to calculate? We could either calculate the OH minus first, or we could go right to calculate the pH. It would seem silly to try to calculate the pOH at this point because we're going to need the pH or the OH minus to do that. So let's say, given the H plus, we want to first calculate the pH. So we're going to stay in the right-hand lane. We know the H plus, that's given. We're going to stay in the right-hand lane. And it shows us exactly what equation to use. So in order to calculate the pH, given the H plus, which is the same as the hydronium, that equals 5.4 times 10 to the negative 4th molar. The map says that the equation to use to calculate the pH is going to be the negative log of the H plus, which we have. So the pH will then be the negative log of 5.4 times 10 to the negative 4th. All right, now I know that many of you have never used the log function before. It's simply a button on the calculator. So in your calculator, everybody go grab a calculator. Pause the video and grab a calculator. You're going to hit negative, find the button that says LOG, not the natural log, not LN, just the LOG, and then type in 5.4 second EE -4, close parentheses, and you should get 3.27. Now, here's how we do Sig Figs. For pH measurements, this first number out here does not count for Sig Figs. You look at the numbers after the decimal. If you notice our original value had 2 Sig Figs, then we want 2 decimal places. I know it doesn't fit the Sig Fig rules we learned in the beginning of the year, but this is just how it is with logarithmic functions. So I'm not a real stickler for this at this point, but it's a thing. That's how you do it. So we have our pH is 3.27. All right, so now we've got our pH. Let's find the pOH, right? Because it's just a short jump over here. If we stay in the right-hand lane here, we're going to be using this equation up top. So if I want to calculate, let me erase this and make some more room. Do the next one. All right, so I know the pH. I want to find the pOH. I'm going to use this equation. pH plus the pOH equals 14. We just found the pH is 3.27. Well, that equals 14. So the pOH, equals 14 minus 3.27. I just did algebra. Subtract 3.7 from both sides. And now we know our pOH is 10.73. Okay, so we just have to find the hydroxide ion concentration. In order to find the hydroxide ion concentration, we can use the pOH that we just found. So now we know the pOH, and we want to find the hydroxide. All right, you're going to stay in the right-hand lane. And we're going to use the following equation. The hydroxide ion concentration is equal to 10 to the minus pOH. So we know the pOH. It's going to be 10 to the minus 10.73. So in your calculator, you can just hit 10 caret negative 10.73. We get 1.85, 1.86 times 10 to the negative 11th. .86 times 10 to the negative 11th. All right, we're almost done. This first row. We just have to answer the question, is this solution acidic, basic, or neutral? To answer this, I want you to look at your pH value and you're going to use what you know about the pH scale. So our pH value is 3.27. On the scale, that falls under the acidic range. So to answer these ones, you're just looking at the pH. If it's less than 7, it's acidic. If it's greater than 7, it's basic. All right, let's do the next row. Okay, for row B, we're given the hydroxide ion concentration. And we have to fill in the rest of the boxes. So we're starting with hydroxide. Now we could do one of two things. We could first find the POH, or we could find the H+. It doesn't matter which one you do first. They're both okay. So I'm going to take my hydroxide ion concentration. I'm going to first find my POH. All right, so let's go this way. If I want to find my hydroxide ion concentration, if I want to find my POH from the hydroxide, we're going to use the equation that's in the right-hand lane here. POH equals the negative log of the OH minus concentration, which was given. So your POH is the negative log of 7.8 times 10 to the negative 10. When you plug that into your calculator, you get 9.11. Okay, so we've got the POH. Now, let's find the pH. If we're going to find the pH, we can use the equation pH plus POH equals 14. I know that my POH is 9.11, so that means the pH plus 9.11 equals 14. Subtract 9.1 from both sides, and your pH equals 4.89. Pretty easy. Okay, now if we have our pH, we know the OH minus, I know the POH, I know my pH. I just have to find the H plus. I can find this by either using the pH or by using the OH minus. That's up to you. I'm going to show you how to do both ways. So first, let's use the pH to find the H plus. Stay in the right-hand lane, and it tells you what equation to use. So I know my pH is 4.89. That means the H plus is going to be 10 to the minus pH. All right, so let's plug it in. 10 to the minus 4.89. So your H plus is 1.3 times 10 to the negative fifth. Now, if you put these in your calculator and you get a slightly different answer, it could be just rounding. Don't worry about that too much. Just worry about learning how to use your calculator and use these equations. All right, so our H plus is 1.3 times 10 to the negative fifth molar. That's a concentration. Anytime you see brackets, it's concentration. So finally, is this solution acidic, basic, or neutral? Well, you're going to look at the pH value. The pH was 4.89. That falls in the range of an acidic solution because it's less than 7. Moving on to 16.5. 16.5 deals with strong acids and strong bases. You already know a lot about these. You know your 7 strong acids, and you know your strong bases. I think there's 8 of them. It's your group 1 and your Castro-Bear metal hydroxides. All right, know them. Make sure you review them. You're going to need to know them for this section. We've already discussed that strong acids ionize 100%, and so do strong bases. Strong acids give rise to H+ or hydronium ions, and strong bases give rise to or produce hydroxide ions. So this statement here, that the equilibrium constant for a strong acid or strong base is undefined, you don't have to worry about that too much at this point. We'll talk about that a little bit later. So the H+ and hydroxide for a strong acid, strong base is determined completely by the stoichiometry of the reaction. That's the dissociation reaction. So let's take a look at a few examples. Let's say we wanted to calculate the pH of a 0.043 molar nitric acid. We'll be looking at that formula and saying, oh, I know that. That's a strong acid. So to try to understand this problem, let's take a look at the dissociation. I could write the reaction in one of 2 ways. I could say HNO3 reacts with water, one-way arrow, to produce H3O+ and NO3-. We could do that, but an easier way to do this, just remove the water molecule. HNO3 gives H+ and NO3-. Make your life easier. So we know that the concentration is 0.0430 molar. Do you remember when we did ion concentration problems? The stoichiometry is 1 to 1 to 1. So I know that the H+ is just 1 times 0.0430. You just look at the coefficient, molar. And if I want to find the pH, well, I know the H+. I want to find the pH, so use your mole map. The pH equals the negative log of the hydronium, or the H+. So when we plug this in, we get 1.37. Okay, now let's take a look at the next one. Calculate the pH of a 0.02 molar barium hydroxide. That's a strong base. So the pH calculation will not be as straightforward. We're going to have to take a couple extra steps. First, we have to consider the stoichiometry here. Notice that there are 2 hydroxides per formula unit. That's the first thing to notice. Second thing to notice is that the hydroxide ion concentration at best can first only get us to the POH. So we're going to have to do 2 steps. So let's first find the hydroxide ion concentration. We have barium hydroxide. It will dissociate into barium ions and 2 hydroxide ions. If the barium hydroxide solution is 0.02 molar, we're going to look at the coefficients, then the barium ion concentration is 1 times 0.02, and your hydroxide ion concentration is going to be 2 times 0.02, which is 0.04 molar. All right, that's step 1. Find the hydroxide ion concentration. Step 2. look at your mole map. If you know the hydroxide ion concentration and you want to find the pH, you should probably get the pOH first. So let's do that. The pOH is going to be the negative log of the hydroxide ion concentration, which is a negative log of 0.04. When you plug that into your calculator, you get 1.398, or 1.4 basically. Let's work with 1.4. All right, we know the pOH is 1.4. Last step, look at your mole map. You know the pOH, we want the pH. So we just have to go to the left and use the equation pH plus pOH equals 14. I'm solving for the pH. The pOH is 1.4. So your pH will be 14 minus 1.4. Therefore, your pH is 12.60. So it looks like a lot of work, but it's really not that bad once you know how to use the mole map. You'll be able to fly through these. Not mole map, the pH map, sorry. So you'll see lots of these problems. We'll have some more practice with this. All right. Now this is not in your notes. However, this is a problem that you're going to see on the review packet that you'll be working on. This deals with BCA tables, pH calculations, and neutralization reactions. So let's say we mix a strong base with a strong acid, and we want to know what the pH is of that resulting mixture. So if they neutralize each other, the pH will be 7. But if they don't neutralize each other, we have to know what the excess reactant is and how much of it is present in its concentration. So that's why a BCA table is going to be helpful. Notice we have 2 volumes and 2 molarities. Oh yeah, this is a limiting reactant problem. So let's look at our reaction. NaOH, give myself a little bit of room here. NaOH plus HCl will react to give NaCl plus H2O. We set up a BCA table. And remember, with a BCA table, we can only use moles. So let's organize our information, and then we'll calculate the moles of each. Here we have 200 mils of a 3.5 molar. And with the HCl, we have 800 mils of a 1.0 molar. To calculate the moles before, let's use the molarity equation. If I have a 3.5 molar NaOH, and I want to know the moles, that's a solution that's 0.2 liters. So X is going to be 0.7 moles. And we can plug that right into our BCA table. For the HCl, let's do the same thing. It's a 1 molar solution. We want to solve for the moles, so I can put it in the BCA table. It's 0.8 liters. So that's 0.8 moles. So X equals 8. I know the moles. I'm ready to complete the BCA table. So if you notice, the coefficients are all 1. And remember the trick, you take your mole value divided by the coefficients to do the limiting reactant analysis. Well, if they're both 1 to 1, then the smaller of the two is going to be your limiting reactant. So NaOH is my limiting reactant. That means HCl is the excess reactant. By nature of being a limiting reactant, we know that they all go away. That's all gone. And 0.7 times 1 divided by 1 gives me minus 0.7, so that leaves 0.1. Now we could actually stop here. However, if you want to complete the table, you can. Plus 0.7, plus 0.7. All right, so in this problem, we're asked to find the pH of the resulting solution. The only thing that's going to get us the pH is the amount of HCl left over, because NaCl and H2O are both neutral. They're not going to affect the pH. So if I want to find the pH and I know how much of a strong acid is left, right, then our next step is to find the concentration of hydronium. Well, if you remember, HCl is a strong acid and it will break apart 100%. But I only have moles here, so I need the molarity. So in order to get the molarity of the HCl and the hydronium, let's take the moles that were left over divided by the total volume. Total volume goes down here because didn't I mix 200 mils and 800 mils? That's 1,000 milliliters or 1 liter. So the molarity of the HCl is 0.1 molar. My molarity is 0.1 molar, then I know my H plus is 0.1 molar. Now I've got enough information to find the pH. You know the H plus, your pH is the negative log of your H plus. This will be the negative log of 0.1, which equals 1. That's how we solve that problem. You'll see one of these in your review packet.